lecture 26. Yesterday we talked about quenching, and we did an analysis of the limiting process when heat generation was equal to heat loss. And I told you yesterday that even in case of ignition, we can do a similar kind of analysis. But we have to remember that just as quenching is not a steady phenomenon, so quenching is a process in which the flame loses heat as a function of time and also starts becoming weaker and then finally get extinguished. And similarly for ignition also, it is not exactly a steady situation to analyze, but we will take only the limiting situation. We will not do a full transient analysis of what happens in case of ignition. So, if you have, let us say, this zone which has a fuel air mixture, and if you want to ignite it, you probably all know from your previous background in internal combustion engines, or maybe just from general knowledge, that if you give a spark here, it might get ignited. Okay, so a spark plug can be something like this. So this has got one electrode here, it has got another electrode here, and when you give a spark, you are actually placing a very high voltage between these two electrodes, and that breaks the dielectric between these two electrodes, and then there is a spark kernel. Kernel is KERNEL, spark kernel, which gets produced. So that is a small zone here, somewhere here, which is at very high temperature, and it has got active chemical species, it has got ions. Okay. So that high temperature and active species, ions, etc., that will help generate a flame which will later on become bigger. And then if it is an engine, for example, that flame will propagate like this. Okay. Does not have to be an engine, but just as an example, in an engine, that is what we do in a spark ignition engine. So this is one mode of ignition. There can be another mode of ignition. You can, in this fuel air mixture, you can bring a small flame like a pilot flame, and that creates ignition. There are even other modes of ignition which we are not discussing today, but primarily focusing on this spark ignition method. So you have this zone. So you are creating a zone which is at a high temperature and where some active chemical species are produced. So let us say this is the kernel and this is the fuel air mixture. Then what is actually successful ignition? Successful ignition is when this will be able to ignite and give a proper flame, right? When it will be able to sustain itself. So imagine a situation that you have given a spark, you have created this kernel, but this kernel is not strong enough, and it's after a few milliseconds or whatever small length of time, after a small length of time, it gets extinguished. Then that is not successful ignition. In fact, in engines you can have misfiring. So just because you are giving a spark does not mean that it will be successful, right? If it is successful, then it is ignition. Some of you have done combustion experiments in the lab, and you know that we have spark igniters in our lab, and if you press the spark igniters, you can get, depending on the igniter, one spark or maybe multiple sparks also, but they do not necessarily always ignite the mixture, right? So what is successful ignition? Successful ignition is when that spark kernel that you have produced sustains and it actually becomes bigger and then gives you a flame, correct? Now in the process we have to remember that we will try to model this situation and find out something about this zone which we are creating with the help of a spark, the spark kernel. We will probably be advised to calculate some radius of this. Okay. So maybe if you think about it, if the spark kernel is too small, probably it will not succeed. Okay. This is without doing much theory, but probably your intuition will tell you that if the spark kernel is too small, then it will not be strong enough. And does it need to be very large? Probably not. Maybe there is some size for which the spark kernel will be able to grow and give you a proper flame. Okay. So, our purpose will be to get this critical radius of the spark kernel, which actually helps in establishing a flame, which helps in sustaining this ignition process. Now, in Turns's book, he writes it as R critical, but we will just write RC. So, C for critical. And if I write a radius RC, then that means I am assuming that this kernel is actually spherical. But that of course will not happen. You can very well imagine that that is not going to happen, but again it is an approximation. So, we can think of a situation when we will have this zone of fuel air mixture, sufficiently large zone, in which we have created a spherical kernel, and we want to see when it will be successful, when it will propagate, right. So, we understand that smaller radius is probably not going to work. Actually, we do not understand, we just think probably it might happen that way. So, think about it, if it is too small, then what will happen? We feel that if it is too small, it will likely be unsuccessful. The ignition event is likely to be unsuccessful. But is that a correct thinking? And how do you think about these issues? If it is small, then what happens?
It might not come in contact with the sufficient amount of fuel, so as to release the quantum of heat that is necessary to sustain the.
Okay, so area of contact, right? Okay. But we again same argument. Yes, you are right. You are absolutely right. Same sort of argument that we had yesterday. See, we just cannot talk about only the area of contact, because there are two things which will again compete with one another. There is thermal energy release because there is some burning taking place, because in the kernel there is burning taking place. You have initiated that with the help of a spark. So, there is some energy release taking place. Now, if that is small compared to the heat loss, then the ignition event will not be successful, correct? And that will again be determined, like in the quenching case, by the area by volume ratio. And if you have a small kernel, then what do you expect to happen to the area by volume ratio? So, you have a spherical volume, it will be high, isn't it? Because area is 4 pi r squared and volume is 4 pi by 3 r cubed. So, if you take a ratio, it will be proportional to 1 over the radius. So, if smaller the radius, larger is area by volume ratio. So, you expect that for small kernels, the heat loss is likely to be stronger than the heat that is generated, the thermal energy released in the flame. So, we will keep that argument in mind. So, looks like we will have a critical size, okay, below which the kernel size will not be successful in producing sustained ignition. More than this, more than the critical size, it will likely be successful, because then the area by volume ratio has actually decreased. So, the heat loss has decreased compared to heat generation. This is what we suspect. So, again we will use that limiting argument of heat loss equal to heat generation. Now, before we proceed, just one more factor. We will analyze this sort of a situation, large volume of fuel air mixture in which we have a spark kernel, and do the analysis based on that. But of course, you can understand that in reality, if you have a spark plug, for example, giving a spark here, let us say in an engine situation, then the kernel loses heat not just to the gas that is surrounding it, but probably also to the solid of the electrode, isn't it? To the body of the electrode, to the body of the spark plug. So, it will lose some heat out there. So, the gap between the two, if I draw the spark plug again here, this is one electrode, this is another electrode. So, between the two, this distance is also going to matter, isn't it? If the distance is small, then you are likely to have a small kernel with large heat loss, things like that. So, in the spark plug design, these issues are actually taken care of. But in our analysis, there are no electrodes. Our analysis is just like this. So, keeping this in mind, we talk about that kernel zone. Okay, and we call this radius as RC. This is in this larger fuel air mixture. In fact, in the drawing, the kernel is showing exaggerated and it's actually, it appears to be big enough and comparable enough to the fuel air volume, but it's actually not, it's actually very small compared to that. So, this fuel air mixture extends up to large distances. There is no flow in the system. Okay, here we are considering quiescent mixture, there is no flow. In an engine, if you have the spark plug giving a spark and creating the kernel, there is flow. Okay, because there is fuel air mixture in the engine, there is piston movement, there is turbulence, there is a lot of flow happening out there. In a flow situation, things will change. In a flow situation, in fact, this kernel which we produce here, that will tend to get maybe elongated in some direction depending on the flow. Okay, and the flow will contribute to heat loss in some ways. We are not in a position to describe all these things in detail. So, we are taking again as usual a simpler situation where it is just the quiescent mixture, fuel air mixture, you are giving a spark, electrodes are nowhere to be seen, and you have generated this volume which is at a temperature of, let us say, Tb, which is the burnt gas temperature. Okay. So, it is at Tb and it is also reacting and releasing heat, right. And what, so that's within the sphere volume. Beyond the sphere volume, what do you expect? You expect the temperature to go down, right. So, it will go all the way down and sufficiently large distance from the kernel, sufficiently large distance at sufficiently large distance from the spherical volume, the temperature should drop to Tu, which is the unburnt temperature. Okay. So, what is the sort of balance that we do? We will do this is what? There is some fuel burning here that is generating heat. So, it is minus m dot f triple prime bar into delta Hc. How much is what is this quantity? This is per unit volume again, right. This is the heat which is getting released. This is the thermal energy which is getting released because of chemical reaction. Okay. So, the spark has helped it, reaction has taken place, and this is releasing this much amount of heat. And that multiplied by 4 pi by 3 r c cube. Why are we taking RC, R critical? Because we are looking at the limiting situation when heat generation is equal to heat loss. Okay. So, that happens and that will be equal to the heat loss, right. So, the heat loss will be minus K, then area is 4 pi R C squared, and then there will be a dt dr at r equal to RC, correct. So, this is minus Ka dt dr at r equal to RC. So, these two things should be actually equal. So, here comes the next question. How do you get dt dr at r equal to RC? This is heat loss from that spherical volume to the surrounding gas, to the surrounding fuel air mixture, which is at a temperature that is lower than Tb, which has a temperature variation in it. Okay. So, it is Tb at the boundary between the spherical volume and the unburnt gas, but then as you move away from the spherical volume, temperature keeps decreasing, and sufficiently far from the spherical volume, the temperature becomes Tu. Okay. So, the question is, how do you get dt dr at r equal to RC? That is at the boundary of the spherical volume. How do you get that? Okay. So, that is the question. Now, that is not really a combustion question, isn't it? Because there is no combustion happening. beyond r equal to RC.
Can we again assume a linear profile?
There is actually no need to assume a linear profile. Okay. We assumed a linear profile. The question is, can we assume a linear profile? Now, we assumed a linear profile when we were deriving expression for laminar burning velocity, and that linear profile was in the flame zone. Why did we do that? Because in the flame zone, so we're going back a couple of lectures, in the flame zone we know the temperature will vary, and we also know that the temperature will not vary linearly. Okay. So this is a digression, but since the question was asked, I am trying to explain this. So in the flame zone, the temperature variation is not linear, but we kind of expect that there's some rounding off here, some rounding off here, and things like that. But we didn't know how to determine this. Actually, if you want to determine this, then you have to solve a more complicated set of equations. Didn't want to do that, so we took this to be some linear temperature profile. Okay, but that was in the flame zone, right? So that was a combustion problem which we are trying to simplify, and this was part of the derivation for laminar burning velocity SL. Fine. Now, coming back to what we are doing today, we are trying to get dt dr at r equal to RC, correct? Now, that actually is that can be obtained if you get this temperature profile. Okay. Now, where is the r? R is the radial coordinate, so r goes like this. Fine. So, if you get t as a function of r, then you can get dt dr at r equal to RC, and that dt dr has to be looked at from r equal to RC and beyond. There is no point you can't get dt dr by looking inside the spherical volume, because in the spherical volume we have assumed it to be all Tb, uniformly Tb. Okay. Not exactly a perfect assumption, but that is what we have assumed. We have assumed that with the help of the spark, somehow temperature has been raised, and the spark has helped by releasing that much amount of energy, and then there is reaction taking place, and it is all giving you burnt gas temperature. That is the assumption. So we have to solve for this, which we call T as a function of R. Now, this is not combustion, correct? Because there is no combustion happening in this zone. So what do you have here? You have this part, right? That is everything except the spherical volume. In that you have to find temperature. No chemical reaction is happening there. We are assuming there is no chemical reaction happening there, because the chemical reaction has been restricted to the spherical volume where you have used the help of a spark. Right. So how do you get T as a function of R? It's not a combustion problem. That's why I'm asking you, because you must have done some other courses which will help you get this.
Conduction is there, radiation is there.
Yeah. So there is conduction, there is radiation. The radiation part we will neglect. Okay. So we can, if we solve the conduction equation in this part which I have shaded with blue, then you will be able to get T as a function of R. Correct? And it will require some differential equation and some boundary conditions. Where will the differential equation come from? Heat equation, right? Heat equation. So you have energy equation for pure conduction, which is heat equation, written for this blue zone. And it has to be written in which coordinate system? No, not cylindrical, spherical. There is no cylinder here because we have the volume is spherical, so it's all spherical, right? So we can write the heat equation in spherical coordinate. There is no heat generation term, by the way. There is no heat generation term because in this blue zone there is no heat generation. And if we solve that, then you will get T as a function of R. Of course, we will need boundary conditions, and you can actually tell me, if you look at this, what the boundary conditions should be. How many boundary conditions would you need for an equation like this? 2. Okay. We expect this to be second order in temperature, and you need 2 boundary conditions. And can you see the boundary conditions? Correct. So, at r equal to RC, T should be equal to TB, and r tending to infinity, T should be equal to TU. Right. So, we will do that, and the equation, as you probably be able to write. So, if you remember your conduction, then we should be able to write this. There is no heat generation term, heat equation in spherical coordinate, steady state, not transient. And this one, with a little bit of effort, this okay, let me write the boundary conditions also. R equal to RC, T equal to TB, R tends to infinity, T equal to TU. We can get T as a function of radius, something like this. So, I am now actually not doing this part, not doing the derivation, it is very simple integration. So, when you integrate, you will get C1 and C2, and you evaluate those C1 and C2, the constants which come because of the integration using these two conditions, and then you should be able to get this. K is thermal conductivity, yeah, K is constant, thermal conductivity is taken to be constant, thermal conductivity of the fuel air mixture is thermal conductivity of the fuel air mixture, because the domain, the one which I marked with blue, is actually a fuel air mixture, right. In fact, this will be close to the thermal conductivity of air, because fuel is always small compared to air. And dT dr at R critical is this. This is dT dr. So, we now know what to do. So, this you have to verify, of course. I have verified myself, but you need to do this yourself. So, leave some space in your copy and do this. So, this we want to use, and let us go back to the limiting condition that we had for this spherical volume. We wrote, so this is radius R C, this is some general R, and we wrote minus m dot f triple prime bar delta H C 4 pi by 3 R C cubed is 4 pi R C squared K dt dr at R C, correct. This was the balance few minutes back, we wrote that few minutes back, and now we have dt dr at R equal to R C. So, dt dr at R equal to R C is minus Tb minus Tu divided by R critical, right. So, this two minuses will make this plus, and this is Tb minus Tu by R C. And just following up on what we did yesterday for quenching, you know now next what steps to take, right. So, minus m dot f triple prime bar will come from that SL expression. SL, we know that we have an expression for SL which we derived some time back. So, we have SL like this, and we will also write delta Hc as nu plus 1 Cp Tb minus Tu, correct. So, we will utilize these here, and okay, first from here we will be able to get, let us say, this box here, which tells you that R c squared is 3k Tb minus Tu this, and in this we can put those expressions. So, again everything requires verification, you should be able to verify all this. And with a little bit of work after this, R critical comes out to be root 6 times alpha by SL. And that is of course root 6 divided by 2 into delta, correct. So, the critical radius has to be more than the flame thickness. Like in the quenching analysis, where we got the quenching distance to be equal to square root of b into delta. So, here also we got the critical radius for successful ignition to be square root of 6 by 2 times delta. So, it has been obtained in terms of delta. Now, delta can be calculated. Delta can be calculated because we have done this before. Delta is 2 alpha by SL, and SL we can get for various kinds of mixtures. Actually, we have the simple theory which will give us delta, or even otherwise you can also get SL values from correlations, let us say. I just mentioned a couple of classes back that there are burning velocity correlations in the book. So, using those also for various conditions you can get burning velocity, and once you get burning velocity you can calculate the flame thickness as 2 alpha by SL and then multiply it by root over 6 by 2 to get the critical radius for ignition. Now, this is again all this analysis that we are doing definitely not all that accurate, but it gives you an idea that this should be somewhat more than the flame thickness.
Yeah. What will be the SL here? How the kernel radius is increasing? DRDT, that is the SL.
No. SL is the fundamental property of the fuel air mixture. SL is the fundamental property of the fuel air mixture. So, again, like just to give a concrete example. So, if you have, let us say you have methane air mixture, 1 atmosphere, 298 Kelvin, equivalence ratio of 1, then regardless of the situation we know that there is a property called SL, which is laminar burning velocity, which is 37 centimeters per second, okay, 0.37 meters per second. So, we will use that value in here. So, this is not, so the question was, is it equal to, is SL equal to drdt? No, drdt in any case is kind of like a spatial speed, and we know that spatial speed and burning velocity are not the same. Burning velocity is transformation velocity, which is not necessarily equal to the spatial speed. Okay. So, we will just treat this as a property. SL will treat SL as a property. Remember that for a fuel air mixture, its laminar burning velocity for a given set of conditions is actually just one number. So, whether it is a planar flame propagating in a channel like what we were seeing yesterday, in our quenching analysis, there is a slab, there is a sheet of flame which is propagating between two plates. Now, today we have a spherical flame which is trying to get bigger, right. So, these are different configurations, but in all configurations we can use SL because SL is a fundamental property of the mixture. And just to remind you, we say that this is a property of the mixture because it's not configuration dependent, it's actually not dependent on the fluid mechanics also, as long as the flow is laminar. Okay. So, SL is laminar burning velocity, it's a property. There is also turbulent burning velocity, it's not a property of the mixture. Okay. Turbulent burning velocity depends on the flow situation, depends on the configuration, things like that. We haven't discussed turbulent burning velocity, which if time permits we will do that to some extent. Okay, so we are using this just as a property, and this will allow us to calculate the critical radius for this ignition process. So, we can calculate RC. Now, another interesting thing that we can do from here is that we can also calculate minimum ignition energy. So, if you have heard about this, if you have done a course on engines, for example. So, the minimum ignition energy is the energy that you give to raise the temperature of a fuel air mixture from TU to TB, like this spark kernel, the spherical volume which we are looking at so far, was initially at a temperature TU, and it has been raised to TB, and now it's burning and it's releasing heat. Now, it requires a certain amount of energy to be given to a volume of radius RC to be raised to temperature TB. So, that energy is a minimum ignition energy. Why are we calling it minimum ignition energy? Because it corresponds to the critical radius. We could have given more. We could have given more than the minimum amount of ignition energy. In that case, we could have got a larger volume inflamed. So, we could have got a radius larger than RC if we wanted. So, that is also ignition energy, but that is not the minimum ignition energy. So, the minimum ignition energy will correspond to the critical radius of ignition. Okay. So, how to calculate that? The ignition energy will be m corresponding to that critical volume, mass corresponding to that critical volume, then a Cp which corresponds to burnt gases, multiplied by Tb minus Tu. Okay. So, what we are saying is this volume, think about this spherical volume, this was initially at temperature Tu, now it has been raised to temperature Tb. Who has done that? The spark has done that. Okay, some ignition agent has done that, and it has done that, it has been able to do that by using some energy, and that energy is this much. Okay. And we can now in fact calculate this, because this m critical must be 4 pi by 3 RC cubed into rho b into Cp into Tb minus Tu. M critical must be this. So, at temperature Tb, we are considering this gas to be having a density which is rho b, the burnt gas density. We already have an expression for Rc in terms of delta, or you can say in terms of alpha by SL. So, if we place this in the expression that you see here, if this Rc is utilized here, that Rc is utilized in here, then we should be able to get ignition energy in terms of laminar burning velocity, correct. So, that is this. Now, Rb is a burnt gas gas constant. Okay.
61.6 P.
61.6 times pressure. Okay. So, you can ask the following question: where does the pressure come from? What do you think? Burnt gas density. Burnt gas density can be written in terms of pressure and the characteristic gas constant for the burnt gas. So, the characteristic gas constant for the burnt gas is the universal gas constant divided by the molecular weight of the burnt gases, which we are calling Rb, and that Rb is showing up here. Pressure, same on the burnt side as on the unburnt side. So, we do not write P subscript B, isn't it? What is the reason? Because we are talking about deflagrations. For deflagrations, there is hardly any pressure difference between the unburned side and the burned side, correct? Remember the Rankine-Hugoniot that we studied, the point corresponding to typical deflagration is, I mean, it gives you a P2 value which is almost equal to P1, right? Okay. So, this is ignition energy. So, this ignition energy expression is useful because using this you can calculate for a certain fuel air mixture. You may have a fuel air mixture that you are trying to ignite. So, this expression will tell you how much energy, minimum how much energy will be required to ignite that particular fuel air mixture. In practice, of course, see, in practice you have electrodes which will suck in certain amount of heat, because I just told you that the analysis that we didn't have the electrodes, didn't have the body of the electrodes. If you have the body of the electrodes, then some amount of heat will go in there. Then in practice there is also flow. If there is flow, then there can be effect of stretching the kernel. The kernel might become longer in a particular direction, and it may become thinner at certain areas. So, it might become more difficult for the kernel to survive properly, plus the heat transfer might also change because of the flow. So, keeping all this in mind, many practical issues, the minimum ignition energy which you calculate using this particular expression is still kind of an underestimate. So, in practice you have to give somewhat more than that. Okay. So, then what is the purpose? If again this is not very accurate, then what is the purpose? At least one purpose is satisfies very well. It tells you how the ignition energy should depend on pressure or temperature, the unburned gas temperature. Okay. So, when it comes to pressure, can we say that the ignition energy is just proportional to pressure? Higher the pressure, more the ignition energy. Actually, that is not correct. Pressure is hidden somewhere else also. Yeah. So, pressure is hidden in an alpha. Actually, in SL also. SL is also pressure dependent, but SL's dependency on pressure is somewhat weak. Correct? SL's dependency on pressure is weak. So, if you neglect that, still you will have dependency of alpha on pressure. Alpha is K by rho u Cp. Okay. K is not really dependent on pressure. Okay. Rho u is dependent on pressure. How? Through ideal gas law. Okay. So, that means you can expect a pressure dependence of P to the power minus 2, pressure to the power minus 2, looking at this expression. Why?
Temperature, Cp, Rb, all the terms are also there.
Yeah, but we are as of now just talking about pressure dependence. So, the pressure dependence is actually, pressure dependence is here and here and here. If we neglect the pressure dependency of SL because it is weak, then it depends only on alpha. Alpha is K by rho u Cp. So, rho u goes up. So, it is rho u cubed. Rho u is proportional to pressure. So, it actually total it will give you P to the power minus 2. Okay. Rho, so alpha is K by rho u Cp and pressure equal to rho u R u T, from that sort of thing. You can see that you have P to the power minus 3 coming because of this, and then there is a pressure. So, it is P to the power minus 2. So, E ignition is proportional to P to the power minus 2. Actually, the good thing is people have done experiments and then they have seen that this dependence is really very accurate, okay, even though our analysis is simple. So, ignition energy does depend on pressure in this fashion, inversely proportional to pressure squared. You increase the pressure, ignition energy in fact comes down. What about temperature? If you increase TU, what will you expect? Lower ignition energy, because actually if you increase TU, reactions will become easier. So, it's kind of clear that if you increase TU, it will be easier to ignite. So, even without looking at the expression, I think we can posit that. So, that's possible. What about equivalence ratio?
Ignition should be high with either side of the equation.
Yeah. So, if you, for example, if you have a lean mixture close to flammability limit, you have to give more energy, and you can show that from here, because it's proportional to SL to the power minus 3. Ignition energy is proportional to SL to the power minus 3, isn't it? So, SL value is smaller if you go to, let us say, very lean mixtures or very rich mixtures. So, there will be an issue there. So, especially lean mixtures, it will require more energy. Okay. So, this is what we learned from the analysis of ignition energy. Pressure dependence P to the power minus 2 is actually very accurate, and the expression that we got will probably do some problem sometime to calculate the minimum ignition energy. The expression that I got, I am writing it as E subscript IGN ignition energy, but it is actually minimum ignition energy, because we did a limiting analysis. More than this is ignition energy, but not minimum ignition energy. Okay, so, this is about ignition. We understand that we have considered quiescent mixture. In reality, there is flow, and we did not consider, so flow we did not consider, electrodes, okay. And as usual, we did not look at the transient nature of the process. A lot of things we did not do, but whatever we did, that gave us some physical idea of the situation. So, after laminar burning velocity, we are discussing premix combustion. After discussing laminar burning velocity, we talked about quenching yesterday, and we also talked about flammability limits, and today we have spoken about ignition, right. But there are other phenomena which we want to cover, and we have just sufficient time to start that discussion today. So, we will talk about flame stabilization. Flame stabilization is typically very interesting in the premix flame context. Even for non-premix flame context, it is interesting, but in case of premix flames, I think it is more critical quite often. Again, we will think about some of the videos that we have seen before, and we have seen the flames can flash back, and then flames can get lifted off the burner, and flames can get blown off, right. So, when I talk about flame stabilization, we will try to understand when does the flame get lifted from the burner, when does the flame get blown off, and also when does the flame travel back inside the burner. Okay. Some of that understanding we have already developed because we are discussing quenching and things like that, but that discussion is not complete. So, we will take that discussion up, entire flame stabilization discussion up from now onwards. Today, in the limited time that we have, we will talk about stabilized flame, and then slowly we will go towards situations where the flame does not remain stable, does not remain anchored on the burner. So, this is a tube burner. Again, in this course often I am drawing tube burners, but actual burners can be much more complicated than this. But of course, we cannot go to actual burners with more complications and let us say swirling flow in it, or different kinds of port arrangements, lots of other complications which people use. We cannot use that now. So, just looking at a very simple situation. It is like a Bunsen burner, and we have seen again some examples of Bunsen flames. So, we know that we get flame like this, and that flame, the edge of the lower edge of the flame is very close to the top of the burner. So, that is the burner rim. So, it is very close to that. So, if it is very close to that, then we call it a stabilized flame. And we also know actually that there can be a diffusion flame zone, non-premixed flame zone just outside it. If something is not burning in the premix flame, then it can go above that and burn there. So, we typically can see two flames, but we are primarily focusing on the premix flame now, and we are primarily thinking about situations which are for laminar premix flames, because these are easier to understand. So, once we finish this, we will try to go to turbulent premix combustion also, to a limited extent, because we may not be able to spend a lot of time on that. Okay. So, what are the questions that come to your mind if you look at a figure like this? So, one question probably, I am guessing, is why does the flame appear approximately conical? It is not exactly conical, but why does it appear approximately conical? How does it become like this? Okay. Actually, some of you may have done experiments in the lab when we have taken photographs of this premix flame, and from that we got the treating this as a cone, treating this flame as an approximate cone. We have measured, maybe from a direct photograph image processing, or maybe through some optical methods like Schlieren method or shadowgraph method, we got this half cone angle which we call alpha. Some cases we have got that, and from that alpha we, in those lab experiments, for people who have done that, they have obtained an estimate of the laminar burning velocity. Okay. So, this, some of you may be familiar with this, but then that does not answer this question, why does the flame appear to be conical? Okay. It is definitely very close to being conical. So, why is it conical? Okay. So, that is one question. So, the next question is, I have already mentioned that in some situations the flame flashes back, so that it goes inside the burner. So, why does it flash back, and when? So, why and when? And then lift off. Lift off means the flame is still there, but it is kind of lifted up. So, this gap is significant now, easily observable. So, this is a lift off situation, and then, so again the same why and when, why do you get this lift off, and also for blow off. Blow off means that the flame just extinguishes. So, typically what happens is, answering the when question, typically what happens is that if you have a stabilized flame and then if you increase the flow rate, at some stage it gets lifted. I am talking about the flow rate of the mixture, and if you increase the flow rate even further, it will get extinguished. Yeah, again we kind of know all these things. Now, we should be able to explain all this. So, the first question is, why is it approximately conical? It is conical, drawing it as a conical flame. What happens is, we have probably used this expression some time back, SL equal to VU sin alpha, where this is alpha. Did I write this before? Yeah. So, what is VU? VU is the unburnt gas velocity, typically at the exit of the burn. Okay. Now, let us think about the unburnt gas velocity at the exit of the burner. Is it one value VU, or does it have a distribution? Does it have a distribution, or is it one value? Depends on the burner design actually. In a tube, typically there will be variation of velocity, and there will be, it may look like a parabolic velocity. but you can actually use a sharp edged orifice to get a more uniform velocity pattern. Okay. So, if Vu is more like this, uniform Vu, then SL by Vu is also uniform, correct? So, what do we mean by that? SL is, for a given fuel air mixture, SL is one number, like what I was saying, that a 1 atmosphere 298 Kelvin methane air equivalence ratio 1, that is stoichiometric mixture, SL is 37 centimeters per second. Okay. So, just one number, SL is one number, and if Vu is uniform, then SL by Vu is also just one number. So, in that case, you will get a constant value of sin alpha, and then you get a sharp cone, constant alpha. So, SL by Vu uniform means constant alpha, which means a sharp cone. Okay, what do we mean by a sharp cone? In an actual geometrical cone, looks like an actual geometrical cone. But if alpha varies on the surface of the cone, it is not really a sharp cone. If alpha varies on the surface of the cone, then it is not really a sharp cone, in the sense that if there is variation of Vu, or if there is variation of SL, and if SL by Vu is not uniformly the same value, then it is not really a sharp cone, correct? So, that is possible. So, in reality, flames are not actually sharp cones. So, what we have just seen here is that if Vu is uniform, and if we can say that SL is just one value, then the flame will give a sharp conical surface. Okay. But at the first place, why is it conical? And we started from here because this is something which I had already told you. But at the first place, why is it conical? Is it possible to get some other shape which is not conical? See, actually what he is trying to do, what the flame is trying to do, is that it assumes a shape which gives a Vu's component, unburned gas, normal component of the unburned gas velocity equal to its laminar burning velocity. That is what it is trying to do. So, what is burning velocity? Laminar burning velocity? Laminar burning velocity is with the velocity with which the unburned gas moves into the flame, normal to the flame and relative to the flame. So, as you change the velocity through the tube, if you change the velocity through the tube, the flame kind of adjusts and tries to always produce a surface where the unburned gas normal component of velocity becomes equal to the laminar burning velocity. Now, let us try to understand this a little better. If you are able to make, let us say you have a tube, and somehow in a tube it will not happen typically, but let us say if you are able to make Vu equal to, let us say 37 centimeters per second. Let us talk about that same methane air mixture. In that case, what kind of flame you might get? Will it look conical? Actually, it did not look conical. What is the flame trying to do? SL equal to normal component of Vu, but Vu itself is 37 centimeters per second. Okay. So, can the flame be like this? So, the unburned gas is moving into the flame at 37 centimeters per second. That is satisfying for the flame, because the flame has its inherent property which is laminar burning velocity, which has to match the normal component of the unburned gas velocity. So, it can give you that, but the trick is that in real life it is very hard to get this uniform velocity at 37 centimeters per second produced on a burner, which will give you a flat flame like this. Okay. So, it is hard, but it is actually possible. Now, if you increase the velocity, if it is more than 37 centimeters per second, so close to 37 centimeters per second, but more than 37 centimeters per second, then you will slowly start seeing that the flame becomes like this, small flame like this, okay, with this large value of alpha. All right. If we increase the velocity further, what will happen? The flame height at the center line should increase, isn't it? So again, it's like from intuition, it's possible to say such things. Of course, intuition itself may not be always enough. We have to see whether it's logical or not. So if you increase the velocity, you will get a flame like this. So what has the flame done? Because now the velocity is maybe 55 centimeter per second, the flow velocity Vu. Then it's now sin alpha is SL by Vu, so it's 37 by 55, which is almost like 2 by 3, isn't it? 37 by 55 is almost like 2 by 3. So sine inverse of that, whatever it comes out, that's the alpha that it produces. And if you increase it further, it will still give you a sharper cone. So it's always trying to adjust its shape so that the normal component of the velocity becomes equal to SL. Why is it trying to do that? Because that's the rate at which it can consume the fuel air mixture. It has this inherent limitation. It can do only 37 centimeters per second. That 37 centimeter per second of SL translates to some mass consumption rate. M dot double prime is rho u into SL. So it can handle that mass consumption rate of rho u into 37 centimeters per second. So it's trying to get the flow equal to that, and it's adjusting its shape. So it's a nice thing that it is doing. It's doing it on its own, right?
So can you relate this flow to the internal flow of the fluid through the pipes? Like because it due to boundary layers and all, it becomes parabolic in the circular pipes. So in the center, the speed is always maximum. So accordingly, in the center part, since the U is high, that's why it goes to the longer distance, and the surface part is shorter distance. That's why the profile is.
Okay, the question here is that for flow through this tube, there is a velocity variation. So the maximum velocity is expected at the center line. Flow velocity, maximum flow velocity is the center line. So the question is that what is causing the flame to be tallest at the center? Actually, the reason why I was discussing a few minutes back that if Vu is uniform, then we get a very sharp uniform cone. The reason I mentioned that is that the conical shape is actually not dependent on the parabolic velocity profile. Okay, even if you get this parabolic velocity profile with a high velocity at the inlet, of course you can get conical flame. We still haven't discussed that. I am saying that even if it is uniform flow, you still get a conical flame, because the flame is adjusting its shape so that it can consume the fuel air mixture properly. Okay, so we will come to that velocity variation issue also. And we will just close in a minute. If we increase the velocity further, it will become still a sharper cone, but beyond a point, the flame cannot adjust like that. The cone angle becomes too small, and after a while, its flame gets just lifted off. It cannot continue just becoming taller and smaller half cone angle. It cannot do that. Okay, so we are running out of time. Since we are running out of time, we will stop here. In the next class, we will start from this discussion, and then maybe understand lift off and blow off, and then go to flashback also. Thank you.